Hello. So we've seen what inflection points are, but sort of as usual, we want to find a way to find these points rigorously, or in other words, we want to solve them algebraically. So our goal in this video, develop the mechanics and the results necessary to find and verify an inflection point. So inflection points. So remember, inflection points represent this transition point between concavity, right? So the easiest way to think about them when we're trying to do the mechanical part is to consider the parallel between them and the local extrema example. So when we were doing local extrema, we said, okay, local extrema occur at critical points, but really we want to know, okay, they occur if the first derivative changes from positive to negative or negative to positive. Inflection points occur if the second derivative changes from positive to negative or negative to positive. So essentially the process for finding inflection points is identical to the process of finding local extrema. So with this in mind, we can sort of go through the definition here of the inflection point, which again, I will sort of translate into human speak. So inflection points, if we have a function that is second differentiable, meaning you can take a second derivative, and we have some value in the domain C, and we know that that second derivative is 0, we say that that value, that C value, is an inflection point if the curvature of the function changes, right? If the sign changes across C. So what this is really saying is that if we have a point in the domain of a function where it makes sense to talk about this, right? We can take a second derivative, and we have a point in that domain, then that thing is an inflection point if the concavity changes at that point, going from, say, concave up to concave down, or concave down to concave up. So exactly sort of what you would expect given everything we've said before. So this means, though, that the process of finding inflection points is the same as the process of finding local extrema. The only difference is that we're using the second derivative instead of the first derivative, right? So we start by computing the second derivative, finding the zeros and domain restrictions in that second derivative. Then we form a sign chart, right? Again, for the second derivative rather than the first. Then at any of the points on our sign chart that were zeros of the function, we want to check the sign to see if the sign changes either from positive to negative or negative to positive at that sort of zero, at that point. And if it does, that's a point of inflection, okay? So it really is the exact same process as finding the local extrema, and the nature of that is telling us exactly the same thing, right? So we're knowing if it's an inflection going down to up or up to down. The only difference here is we're using the second derivative instead of the first. That's the only difference. All right. So what did we do? Well, we discussed the formal definition of the inflection point, which really just ended up being it's exactly what you'd expect it to be, albeit in a little bit more dense math speak. And we discussed the approach to finding inflection points, which again was pretty much exactly what you'd expect it to be. It's exactly the same process as finding the local extrema. It's just that now we're doing it with the second derivative instead of the first. Okay. So that's that.